Hello everyone, and welcome to this 8th video that will be part of the series about abstract algebra. And as promised in the last video, today we will look at the fundamental theorem for cyclic groups, which is a very important result in abstract algebra. And so let's start by stating it, and then we're going to prove it. So let's suppose that G is a cyclic group. So I'm just going to write G is cyclic. Then every subgroup of G is cyclic. And let's call this part 1 actually, because we're going to subdivide this proof in various parts. And let's prove part 1 specifically. So we just suppose that G is cyclic. So in other words, G cyclic is the same thing as saying that, well, G can be written as the cyclic subgroup generated by A, where A is one of its elements. Okay, but now let's suppose H is a subgroup of G, and here we're going to suppose that H is not equal to the trivial subgroup, because, well, in the case in which H is a trivial subgroup, then H is trivially cyclic. So we're going to exclude this possibility. So in other words, we will have that there is at least one element in H that is not the identity. Okay, but all elements of G are of the form a to the L, where L is an integer. So we will have that being H a group containing an element other than the identity, so an element different than the identity, and being a subgroup of G, it will contain, so H contains an element, at least an element of the form a to the k, where k is a positive integer. Well, the fact that it's a positive integer follows from the fact that if, well, in general, it contains an a to the m, where m is an integer. But if this integer m would be negative, then by the fact that H is a subgroup and that it contains the inverse of each of its elements, then it would also contain a to the minus m, and minus m will be greater than 0. So we will have that, in general, our subgroup contains an element a to the k, where k is a positive integer. So now what we want to show is that our H can be written as the cyclic subgroup generated by an element a to the L raised to a positive integer L. Okay, but let's also specify what this L should be in particular. The L should be the least positive integer such that a to the L is an H. Okay, let's start by proving the reverse inclusion. So let's suppose well, we have this a to the L. Well, since a to the L is in H, then all the powers of a to the L are in H, since H, being a subgroup of G, is a group in its own right, and thus it is closed under the operation with respect to which it forms a group. And so we will have that, in general, a to the L to the m, where m is an integer, is in H. But this is the same thing as saying that a to the L as a cyclic subgroup is a subset of H, because this is precisely, by the definition of cyclic subgroup generated by a to the L, this is precisely a to the L to the m, where m is an integer. And so we have established the first inclusion. So now for the other inclusion, the direct inclusion, we could say, let's take a general element of H. So a general element of H is of the form a to the, we could say, L tilde, where L tilde is an integer, and it is an element of H, of course. Now, by the properties of the integers, and this is a number theoretic fact that is pretty well known, by the division algorithm, we can find integers q and r, in other words, the quotient and the remainder, such that we can express L tilde as L times q plus r, where r is less than L, but it's greater than or equal to 0. Okay, but if we have this, then we can write a to the L tilde as a to the LQ plus r, which is a to the LQ times a to the r. But now, multiplying both sides by a to the L q to the minus 1 yields a to the r is equal to a to the L tilde a to the L q to the minus 1, which is just a to the minus L q. That is a to the L tilde a to the L to the minus q, where here, of course, q is this is the quotient. Okay, but we have obtained this equality here. Now we know that a to the L tilde is in H by hypothesis here, so we supposed it up here, and we know that a to the L is in H by the very way we defined our L, and so we have that, well, a to the L to the minus q being a power of this a to the L by the closure of the subgroup H is of course an element of H itself, and so we'll have this again by the closure of H is also an element of H, and so a to the R is an element of H. Okay, but now notice that R is strictly less than L, but up here we define L as the least positive integer such that a to the L is in H. Okay, but what does this tell us? This tells us that R then necessarily has to be equal to 0. Why? Because, as we said up here, the least positive integer such that a to the L is equal to 8 is in H. It means that all the positive integers before L are not in H by this supposition. And so what follows from this is that we can write L tilde as L times Q. Okay, but then we get that a to the L tilde can be written as a to the L to the Q. But then this is just trivially an element of the cyclic subgroup generated by a to the L being a power of a to the L, in particular the power of a to the L to the Q. And so from this it follows that the cyclic subgroup generated by a to the L is equal to H. In other words, H is cyclic. And this concludes the proof for this fact. In other words, we have just proven that every subgroup of a cyclic group is cyclic. So now we're ready to prove the second part of the theorem. So theorem, let's say theorem part 2. And this part is also very important. And what it states is the following. So if again our subgroup G, which is generated by A, has order n, then the order of any subgroup of G is a divisor of n. And for each one of these divisors that we can call R if you want, this subgroup is unique, and in particular it is given by the cyclic subgroup generated by a to the n over R. So let's prove this fact. Okay, so let H be a subgroup of G. Then by the procedure we can write H as the cyclic subgroup generated by a to the L, where L is a positive integer. In particular, it is the least positive integer such that a to the L is in H. And we have also seen that for all small h in H, we can write small h as a to the L to some q, which is where q is an integer. Okay, but now being H a group, the identity is of course in H. But the identity, since we have supposed that the order of G was n and that the generator of G was A, is precisely equal to a to the n. And so what we have is that a to the n, which is the identity, which is an element of H, and being an element of H, it can be written as a to the L to the Q. But putting the exponents equal to each other yields L times Q is equal to n. In other words, L, which is the order of H, divides n, which is the order of G. And so we have reached the proof for the first part of this second part of the theorem. So for the remaining assertion, which is the uniqueness of the subgroup of such order, we will now proceed to prove this fact. We will now proceed to prove it, and as we can see, it is pretty straightforward. Being R a divisor, of the order of G, we have that A to the n over R is a cyclic subgroup of order R. Well, why is that? Because by a fact that we have proven in the last video, you can recall that this is precisely given by n over the GCD of n and n over R. But this just yields n over R, which is just R. So now all we need to do is suppose we have another subgroup that we can call V, so subgroup of G, such that its order is equal to R, and then we want to show maybe in some way that it is equal to this cyclic subgroup generated by A to the n over R. But how can we do this? So by the previous theorem and by a fact that we used in proving this first assertion too, we know that V can be written as A to the L tilde, where L tilde is a positive integer, and remember L tilde is least positive integer such that A to the L tilde is in V, and so V can be written as this in this cyclic manner like this. We have now supposed that R is the order of V, in other words, is the order of this group here. But we know that we have an expression for this order, and this is particular n over the GCD of n and L tilde. But recall that L tilde is a divisor of n, and from this it follows that the GCD of n and L tilde is just L tilde, and so this expression becomes n over L tilde. But now looking at the right hand side and left hand side of this equality, by the transitive property, it follows that R is equal to n over L tilde, or in other words, L tilde is equal to n over R. But notice, in other words, V is the cyclic subgroup generated by A to the n over R. But look at this, this is precisely the subgroup that we claimed it was unique. In other words, we have proven the uniqueness for this cyclic subgroup of order R inside of our cyclic group G. And so this concludes the proof of this theorem. The reason why this theorem is so important is pretty apparent from the things that it assures. In particular, it guarantees that any cyclic group will have unique cyclic subgroups of a determinate order. Not only that, but it also allows us to search for subgroups in a way faster way by just looking at divisors of the order. And for these reasons, this theorem is very, very important, and it has many important corollaries, such as the following. Let's prove this corollary, which is pretty important because it tells us a little bit about the elements of a determinate order inside a finite cyclic group. So suppose we have a finite cyclic group that we can call G, and we can say that it has order n. Well, then we claim that it be a divisor of n, because we have seen by the last theorem that inside of G, where G is this finite cyclic group, there can only be subgroups of order, the divisors of the order, and these subgroups are unique. So let K be a divisor of n, then there are precisely phi of K elements of order K, where phi of K here is the Euler torsion function, which we mentioned in the first videos, but if you don't remember what it is, it's just the function that counts the co-prime positive integers with respect to the integer we're passing in. So in other words, it counts the number of positive integers such that the GCD of these integers with the argument, which in this case is K, is equal to 1. So let's prove it now. And the proof is rather straightforward. We're going to use some facts that we know about finite cyclic groups. So first of all, we know that there is precisely one subgroup of order K, and that is A to the n over K. That is a subgroup of G, and it has order K. So now let's call our subgroup of order K the cyclic subgroup generated by B for simplicity of notation. And well, now we know that if we have another element of a G, say B to the L of order K, well then necessarily we will have that B to the L is the same as the cyclic subgroup generated by B. In other words, it is equal to H by the unicity of this subgroup of order K. But by a theorem that we have proven in the last video, in particular this one, we necessarily require that the GCD of L and the order of the group, which is K, we're considering inside the subgroup H, is equal to the GCD of the exponent of this the right hand side, which is 1, with K, which is just 1. And what we have got so far is that the elements of order K inside G are elements of the form b to the L, where L is an integer and b is where L is a positive integer and b is a generator of H, and such that the GCD of this L with K is equal to 1. But notice that there are precisely phi of K such L's, and with this we have completed this proof. So using this fact, this corollary, we can prove another corollary that is pretty useful too, and that will tell us something about the orders inside a group, but this time we will drop the condition that G needs to be cyclic. So let's just consider a finite group G. Well then, inside G, the number of elements of order K, where K is again here a positive integer, is a multiple of phi to the K. So let's prove it. So again, in the special cases where the group has no elements of order K, or in the case that G is cyclic, we already have a proof. Because if there are no elements of order K, then we will have that the number is 0, which is trivially a multiple of phi of K. But if the group is finite, on the other hand, we have already proven that the number is precisely phi of K, which is again a multiple of phi of K. So now let's suppose G is a finite group and A is in G, and let's suppose that A is order K. Well then, if that is the case, by some theorems that we have proven quite a lot of videos ago, we know that the cyclic subgroup generated by A inside of G, so of course a subgroup of G, and its order coincides with the order of the element, which is K. Okay, but now, since this subgroup here is a cyclic subgroup of G, then we know that there are phi of K elements of order K inside G, inside Langle A wrangle. But now, since G is just finite and it's not finite cyclic, we might have that, there could be another element, B of G, such that B is not in this cyclic subgroup, and such that B has order K. Well then, if that is the case, we will consider the cyclic subgroup generated by B, which is still a cyclic subgroup of G, and it has order K. And then again, inside B, there are phi of K elements of order K by the last corollary. And continuing in this fashion, we continue until we exhaust the number of elements of order K, such that they're not contained in one of these subgroups, cyclic subgroups that we are gradually building. And why do we have the certainty that at one point we will run out of them? Well, because the group is finite, and so at one point we will exhaust them. And so by going on in this manner, we will obtain that in the end, the number of elements of order K is some multiple of phi of K. So it's m times phi of K, where m is the number of steps that we repeated this procedure. So m is a positive integer. And so with this, we have proven this theorem. If G is an infinite cyclic group, then it has only one element of finite order, and that is the identity. Okay, so let's prove it. The proof of this is pretty simple, because if G is an infinite cyclic group, then G can be written as the cyclic subgroup generated by an element A of G, and this subgroup is, so any element B in G can be written as a to the L, where L is some integer. Okay, if we consider B to not be equal to the identity, which is a to the 0, then if we consider the cyclic subgroup generated by B, this is just the powers of B, which is the powers of a to the L. Okay, but by a fact that we have proven in the last videos, since this group is cyclic, then we will have that, is infinite cyclic, sorry, then we will have that, well, two elements. So we can say a to the NL and a to the M tilde L inside the cyclic subgroup generated by B, then these two will be equal if and only if NL is equal to M tilde L. Why? Because, well, A has infinite order. And so a power of A is equal to another power of A if and only if the powers coincide. Okay, but this basically implies that all elements B, which are not equal to the identity, have infinite order too inside G. And so the only element which has a finite order and which generates the trivial subgroup of G is the identity. And so we have concluded this proof. Another interesting fact that I think must be proven is the following. And that is that for any small g in a group G, then the cyclic subgroup generated by G is a subgroup of the centralizer of G. And in order to prove this, we only need to prove that the cyclic subgroup generated by G is as a set, a subset of C of G. Why? Because we already know that C of G and the cyclic subgroup generated by G are in its own right group. And in particular, they're subgroups of the group G here. So how can we do this? So let's suppose we have an element that we can call H inside the cyclic subgroup generated by G, which is the powers of G basically. Okay, but then H can be written as J to the L, where L is an integer. Okay, but notice that an element of the form G to the L trivially commutes with G, because G times G to the L is equal to G to the L times G, which is G to the L plus 1. And so we'll have that H, which is equal to G to the L, is inside the centralizer of G. And so from this, we have that the cyclic subgroup generated by G as a set is a subset of the centralizer of G. But being both of them groups in their own right, this implies that the cyclic subgroup generated by G is a subgroup of the centralizer. And this proves this other fact. As an exercise before we conclude the video, you can try to do the following things, which is using the facts that we have proven, try to find the generators of Z of the addition group modulo 22, as well as the multiplicative group mod 10, and list all the subgroups of any order. So using again the facts about the divisibility of the orders of the subgroup and so on. Another interesting thing that we can do is determine the number of elements of order maybe of order 3 inside D6. In other words, the dihedral group of order 12, or the symmetries of a regular hexagon, and compare it with this corollary here that we've proven. So with this said, I think we have said enough in this video, and in the next video we'll start talking about permutation. So we'll make a quick recap of permutations, and then we will introduce the notion of permutation groups.